Hey everybody, today I will be going over learning target 14, which is about linear approximations. So a linear approximation is a really good application of derivatives and tangent lines, and it's a good application because we can use these derivatives to very closely approximate a function that isn't the easiest to evaluate. For example, in this problem, we're dealing with the function x to the 1/3 power, or the cube root of x. And this can really be a pain to evaluate if you don't have some number in there whose cube root is also a whole number. So like when we're given this cube root of 26, there really isn't a good way to go about calculating that just by hand or in your head rather than, instead of just guessing what number cubed equals 26. So that's why I make these linear approximations. If you stick around for the end of this, I'm going to go through a couple pictures of graphs that really show you what it actually is. So first we need to identify a function, which I guess I already did. Sorry for that. So then that f of x will be x to the 1/3 power, which is the same as cube root of x. Yeah, sorry for the spoiler. Now we need to find a point. And this point is a point that easily evaluates from that function f of x. So I'm thinking of a cube root that I need a point that I can easily take the cube root of. So I'm thinking 27 because the cube root of 27 is 3, and you can check that because 3 cubed, 3 times 3 times 3, is 27. Okay, so we have our function and we have our point. So now we can just go about exercising the things we learned in this class. I guess one more thing, when we have a linear approximation, typically we call it L of x, uppercase L, it's going to be represented by f of a plus f prime of a times x minus a. This is the form of a line. You have a point here, and this is going to be a slope. It's pretty similar to this being mx and this being b, and those are added together. But I'll get rid of those words just to avoid having a jumble there. So, looking at this, we know what a is, and we can figure out f of a and f prime of a by plugging in and also taking the derivative. So first, let's do f of a. This is pretty simple, and I kind of already talked about that. F of 27 is equal to the cube root of 27, because that's our function, and this just evaluates to 3. Now let's look at f prime of a. This will take a little bit more work. That's okay. We've done all the things in this class so far to do this pretty easily. So I'm going to use the function f of x. I'm going to write it in the form of x to the 1/3, so we can use the power rule pretty easily. That means f prime of x will be equal to 1/3 x to the negative 2/3 power for our power rule. Now we need to find f prime of a, and a is 27. So that equals 1/3 times 27 to the negative 2/3 power. Whoop, messed that up. Negative 2/3 power. And I'm going to rewrite this as 1/3 times 1 over 27 to the positive 2/3 power. The reason I can do that is because of this negative exponent here. That just allows us to move this whole thing from the numerator to the denominator. Sometimes people get confused and include everything, but what we're supposed to do is only the value that is being acted upon by this exponent. So that just becomes here. So I can also rewrite this as 1/3 times 1 over the cube root of 27 squared. That's what that 2/3 power means. Take the cube root of it and square it. You could also write it as the cube root of 27 squared, which I noticed a few people did on the most recent checkpoint. That means now we have to square 27 and then take a cube root of that, which probably isn't something that's easily available, inside just pulling it out. So from here, we can evaluate that cube root, which we said earlier was just going to be 3. So now we have 3 squared. This is equal to 1/3, the same 1/3, times 1/9 from 3 squared. This value is then just 1/27. So now I have f of a and I have f prime of a. So it looks like we have everything. So let's write out our linear approximation. F of a, which is 3, plus f prime of a, which is 1/27, times x minus that a value, 27. There we go. That's part A done. Now we need to actually use this to estimate the cube root of 26. This step's pretty easy. All we really need to do is just plug in 26 to our linear approximation. So we'll have L of 26. This is going to be equal to 3 plus 1/27. And then our 26 goes in for x, so 26 minus 27. And then this piece right here, that just equals -1. So L of 26, and I'll write over here that this is approximately, that's what those squiggles mean, approximately L of 26. And I'm going to use an equal sign here because L of 26 equals 3 minus over 1/27. And then some people also wrote it as 80/27. Both are correct, both are fine. We said you do not need to simplify your answer. So there we go. I will mention though, a lot of people, when calculating f prime of a, didn't really simplify this part here. So we specify in part B that you don't need to simplify your answer. That relates specifically to part B. We're expecting this to be simplified because it's a bit of a gnarly form to understand what's going on, but it's really not too hard to evaluate. Now I'll go over just a little bit of explanation of what this actually means. So over here in Desmos, I plotted our f of x function, which is the cube root of x, and I also plotted our linear approximation, L of x. Here it is, and just notice the scale is a little bit wonky, so the cube root of x might not look like how you're normally used to it being. I just made the bounds a little bit funky just to be able to see it easily. So we can see we have the two functions there, and at this point, like pretty much everywhere over here, they're not really close to each other. And that's okay. That's fine, because this is a linear approximation. It's only meant to be accurate at the actual point of interest, which is why we choose that a value be 27, which is pretty close to the x value 26 they're actually solving for. I scroll down here, and here it is super duper duper zoomed in. Just notice these values right here for y. Just very small differences between them. Yet these points, they're still really close with their respective y values. That just shows how good of an approximation this is. It's really cool because like we have the cube root of 26. There's really not an easy way to do that, except if you use a calculator. But as linear approximation, you can get extremely close answers without having to do too much work. I hope this all makes sense. If you need anything clarified, as always, feel free to stop by office hours. And yeah, I hope this